So, welcome all of you. I'm Vijay Rane. I'm a Prime Minister Research Fellow in IIT Delhi, and today we are here to discuss the problem based on the topics covered in the week 7 of the course, essentials of the oxidation reduction and carbon-carbon bond formation reactions and application in the organic synthesis. So today particularly uh, we'll see some organosilicons or organosilane based compounds and reagents and how it is used for the carry out the multiple important reactions. So before going to start the session, does anyone have any problem that we need to discuss before starting the session? Just let me know. So we'll discuss that problem and then we'll move forward. So we'll wait for 2-3 minutes for taking some problem if anyone have, and then we'll discuss the organosilane based compounds and reagents. So please put your question in comment section or just unmute yourself and ask the question. So as we'll start discussing that problem. So in meantime, probably I will start the discussion. So if you have any doubt, just interrupt me or just unmute and ask a question without any hesitation. So, we have already seen many carbon-based compounds and some oxidizing agent. So, different kind of oxidizing agent that we have discussed. Further, we have already discussed the different type of reducing agents. And now we are slowly moving to the carbon-carbon bond formation reactions. And particularly in this one, we'll see in this lecture, we will see some organosilicon-based reagents and how they are get used for the carbon-carbon bond formation and its some application in some examples. And further, we will see some more reaction which involve the carbon-carbon bond formation. Particularly, we can discuss the organometallic couplings so that it will be a kind of good for you to understand the different reactions which involve carbon-carbon bond formation. So, all right. So, moving to the carbon-carbon bond formation. So, organosilicon-based compounds or organosilanes. So sealants are basically silicon-based reagents. Or so we can see we use the generally carbon. We have seen carbon hydrogen-based compounds, and in organic chemistry, we generally deals with the such compounds which involve carbon, hydrogen, oxygen, nitrogens, and some silicon also is kind of a similar compound, similar element, which has the comparable electronegativity. Generally, in this case, we see if you draw the order of the electronegativity in this case, so hydrogen is less electronegative than the carbon, and further carbon is less electronegative than the nitrogen, and nitrogen is less electronegative than the oxygen. So if you compare the electronegativity of particularly the carbon silicon bond, so carbon is more electronegative than silicon. So electronegativity, if you check the electronegativity, so the carbon is more electronegative. That's why the if you see the bond formation in this case, so generally the carbon prefer the if you have some polar bond in this case, carbon, and here there is a silicon reagent. So in this case, the this will be the delta positive and this is the delta negative. So we can able to get the negatively charged on the over the carbon. Generally, in other elements, other compounds which involve the other heteroatoms like carbon, let's say the bromine, or any kind of carbons, let's say oxygen or nitrogen, or any kind of such electronegative element. So in that case, the carbon will be the delta positive, and further this all these reagents will be the delta negative in this case. So this is the benefit of such organosilane compound to use as a reagent. So we'll see that what are some different kind of reactions which are getting used in the some synthetic transformation. So if you look at the bond energy between the carbon-carbon bond, it is generally in terms of, let's say, if you compare in terms of kilojoule per mole, so it will be 370 to 368 kilojoule per mole. This carbon-carbon bond dissociation energy. If you see the compare carbon-oxygen bond, it will be slightly less as compared to the carbon-carbon. So definitely the carbon-carbon bond is much stronger than the carbon-oxygen. Also, you can see a carbon-chlorine bond, which is slightly stronger as compared to carbon-oxygen bond. Further carbon-fluorine bond, which is again quite strong compared to the carbon-carbon bond as well. Because of this, if you compare the size, this fluorine is small in size, and the chlorine, as we move to this is the it will increase the bond length, and as bond length increases, we know the bond dissociation energy decreases. So then the same relation, you can check the between the relation between the fluorine and chlorine. Further, if you see the carbon silicon bond, it has slightly less bond dissociation energy, and which is 320 approx 318 kilojoule per mole. So it is definitely quite less as compared to the carbon-carbon bond, and that's why it is quite useful for the formation of different kind of uh, synthons, we can say. As we heard the word synthon, it is a kind of a structure which form after dissociation of some bond, and which is kind of utilized in the synthetic power transformation. You have heard this terminology in the rate of synthesis as well. So that's the same. All right. So if you look at the some reagents, like how they are getting prepared, these organic sealants, particularly, let's start with the alkynyl sealant. So which is generally R C triple bond C Si, and let's say it is R3, because the valency of silicon is obviously the 4, right? So it is a tetravalent. And if you look at the because if you move to the periodic table, it is carbon, silicon, germanium, tin. So which is in the same period, right, as the carbon. So that's why the valency is also the same for the silicon. So alkyl sealants are readily accessible by the termi metallation. So if you just add the you just need to take the alkyne, and if you add the base, a strong base, let's say in this case it's if you perform the lithiation, let's say add the methyl lithium or the butyl lithium, or also in case of diisopropyl LDA, lithium diisopropyl. So that also leads to the formation of lithiation. So it will give the RC triple bond C Li, and followed by addition of the uh, R3 SiCl. So if you add this reagent, the silyl chloride, so you can able to get the, so in this case it is a trialkyl chlorosilane. If you add this trialkyl chlorosilane to this lithiated alkyne, so you can able to generate the allyl silanes, right? And this allyl silane is, if you just check uh, the product, so this will be the delta negative obviously, and this is the delta positive. So potentially this can further use for the multiple reaction. Also you will see some reactions of this compound. So let's take the one by one. So further, if we add the electrophile, in this case, this is the starting that we have prepared, this alkyl silane. And if you add any electrophile, so where the electrophile goes attack, so electrophile attack at the alpha position, which is that is the position where silicon is attached. So this is the position where the electrophile get attached. And further, generate the positive charge on the beta position to this silicon group. And if you add the any kind of nucleophile, which will attack on the silicon in this case, and silicon which will again lead to followed by the just electron transfer, gives the compound in which the electrophile, in this case we can add the any electrophile here, and which can be at the position as you can see here. So it will give the radioselectively addition at the alpha position. Uh, of the silicon, this alkyl silane. Further, if you see the another reaction, so this kind of reagent, you can see as you see here the electrophile. So if you see the electrophile is let's say acyl chloride and the LCl3, it generate the ketene, not a ketene, it carbon triple bond oxygen carbene, sorry, carbocation, or we can say here the acylium ion, and this acylium ion is a electrophile. So if you use this reagent as like electrophile used in the earlier case, if you just add the electrophile, it will give the addition of electrophile at the and followed by the so the addition of the electrophile which leads to the formation of olefin and workup from the workup it will be give the water. So water obviously the in this case the nucleophile is the water OH molecule, and if you just do the workup it will give the formation of the product which is a ketone in this case, and it is alpha beta unsaturated, that is alkyl substituted ketone. So this also have some different. This is also the important product which is used in the multiple reactions. So this is by this way you can able to generate a ketone which has the alpha beta unsaturated carbon carbon triple bond. Further, if you check some other reactions, so in terms of the, if you check the comparison between the methyl group and the silicon substituted, so I have just taken here methyl, and we'll see the how the product is getting formed. And instead of methyl, if you add the that silicon, then we'll see the how the reactivity is different in the both the cases. So if you add the acid in this compound, starting as the compound A, it will be the, generate the obviously the it will get protonated, right? And since this alpha bit, this is the allylic position, and cation at the allylic position is quite stable. So the SN1 reaction occurs in these steps. So SN1 reaction generates the cation at the allylic position, and this is got some stabilization due to the this what you can say alpha, this double bond which is alpha situated alpha to the carbocation. So that's why it have got the stability, and the reaction proceed via SN1 reaction mechanism. And further addition of the anion, which is from the acid. So this anion attacks on the here in this case attacks on the methyl, and which is so let's say this is alpha and the beta. So this beta bond carbon bond attacks on the electrophilic carbon, which is the cationic in this case, carbocation, and it leads to the bicyclic compound, which involves the six membered, right? So if you just check the cycle, the newly formed two, four, and five, and six. So the six membered ring is getting formed, and this is bicyclic compound is formed with this compound. But instead of if you just replace this methyl with the silicon, so as you seen earlier, so this the silicon we have just replaced, and the same reaction condition. In the first step, it will be obviously the SN1 reaction. It generates the carbocation, and further, in this case, the anion, the nucleophile attacks on the beta carbon. In the first case, it was attack on the alpha carbon, but because of the silicon, uh, in this case, the nucleophile attacks on the alpha carbon, and the attack takes place of this double bond from the position which sorry nucleophile attacks on the beta, and attacks takes place from the alpha. So this alpha carbon attacks on the carbocation. As a result, one ring is getting formed, which is the seven the bicyclic compound form, which is a seven membered ring, right? So that's the reactivity difference between the when we have the silicon substituted alkyne and the methyl substituted alkyne. So further, if we move to the, as we earlier seen, alkyne silane, this is the alkene silane. So it is a double bonded. So the preparation is the, in this case, preparation will be starting from the alkyne, and alkyne react with the triethyl silane, followed by the H2PT CCl, sorry, Cl6 as a catalyst in the IPA, isopropyl alcohol. So it gives the uh, E silane, right? And which is about 77%. it means it is a reselective scene addition takes place. So the hydrogen and the selene comes from the this reagent Si83. So this is the alkyl, sorry, alkene silane. And if you see some reactions of this alkene silane, how they are using in the day-to-day life of the chemists. So this alkyne silane is prepared. Uh, so this is the alkene silane, followed by this the reduction of this alkyl silane. This is the reducing agent that we have earlier discussed, such a reducing agent, right? In the earlier case at the, I think in the week 5 or week 4. So this reducing agent reduces the alkyne to the alkene, right? And this alkene is will be the addition of this reagent will be the scene. So you can see hydrogen and the Al, not hydrogen, it's hydride, and the reagent attached on the same side. And further upon hydrolysis, this entire Al isoterbutyl groups get removed, and it will give the proton in here. It attach the hydrogen in this case, right? So it gives the here. This is the scene silane, right? In the earlier case, we have prepared a trans, that is the E, and this will be a Z, which is referred to the elite. In this case, as we can see, both the groups are on the same side. So by these two methods, we can generate either cis or trans silane, alkene silane particularly. So if you look at the some reaction of this such alkene silanes, so if you add the any electrophile, let's add the acyl chloride. So in this case, added just the acyl chloride, and it gives the formation of the acylation reaction, and the silicon, this entire group is getting replaced by the acyl. So you can add generate the, and also you can see here uh, it can be used for very easily. About 77% alpha unsaturated ketone is getting formed, right, by using this vinyl silane. So the third one is the al allyl silane. So this allyl silane, you can see this is the allylic position, right? So this position is the allylic position. So if you have some uh, let's say allyl species, so we can generate this allele by let's say any we have any kind of allyl bromide. So you can able if we seen earlier, right? Let's say take this example directly. We have the allyl chloride here and add the Mg. This is the Grignard reagent preparation, right? That we already in the Grignard reaction we know how this getting prepared. So if you just add the uh, magnesium in dry ether, so it will be generate the Mg, right? So this magnesium get inserted between this one and followed by the MgCl, and which is then when created with the R3 SiCl. So so this negatively charged attacks on the carbon, it replaces the chlorine and it generates the, this will be the R, right? So this is forms a allyl silane. So this is the also have some synthetic utility that I mean when you use such reagent, then we will discuss this how this allyl silane is useful. So let's take so this allyl silane I also like to inform sorry the add here. So this allyl silane has some unique property. Let's see let's say we have such compound which is the allyl silane, and particularly here it is a bromo substituted. So when you add the magnesium, it generates the Grignards over this place, and this is the such reagent. It's a synthetic equivalent of the dianion, 1,2-dianion. So if you see the how it is useful for further reaction. So if you add the magnesium, then it will be a it generate the Grignard. It will by the in the presence of copper iodide, that is the copper catalyst, it generate the it shows the 1,4 addition, right? Because of this copper, because of the hard stop, that sort of concept. So because of copper, this copper get inside replace this magnesium and it behave as a soft center, followed by thus it adds on the fourth position. which is the alpha, beta position of the alpha beta unsaturated ketone, and it generates a compound is shown here in the 94%. That is a quite good yield, right? That almost quantitative yield. And if you look at the structure, by addition of the AlCl3, what does AlCl3 do? AlCl3 polarize the ketone group here. So once it polarize the ketone, so you can see here it polarize this ketone, and the Cl minus replace from the AlCl3, the which is nucleophilic in nature, with nature which attacks the silicon. So you can see here which attack the silicon further by the bond delocalization takes place over here. So before that there will be first step, which is this attacks on of this uh, gamma carbon to the silane, which attacks here. So it generates a tertiary cation, which is quite stable. And further, upon addition of this nucleophilic chloride to the silicon, it shifts the bond pair between the carbon and silicon to the formation of double bond. So you generate the exo compound, which is shown here, and so it generates this exo compound. So this this AlCl3 and the complex, upon workup, it get clues and almost 94%. So let's say we start from here, and the first step is almost 94%, and the next step is about 92%. So we overall over the how many steps it gives about, so over this one it gives losses about 4%, sorry, the 6%, right? And then here from 94 to again this 19%, almost 90% or greater than 90%, right? So greater than 90% is obtained uh, over these two steps, 90% or more. So definitely greater than 90% over these many steps, and we get such compound. So you can see, so by using such a simple method and by use of this 1,2-dianion, which is obtained from this bromo allyl silane. So this is the 2 bromo, 3 methyls, 3 trimethyl silane, silyl propene. So that's the compound, and this dianion is getting used in this one in the beautiful way. So this is the utility of this allyl silane as well. So we have one example here. Further, if you perform such Lewis acid synthesis, that also is similar with the previous case. So you just add the Lewis acid, let's say LCl3, and let's say acyl chloride. So obviously, what does it do? It gives the electrophilic this carbonyl center, and this allyl this bond pair moves to here, and it attacks from this position, right, to the center, and it gives the 94% of the product. So attacks take place from the beta position. So sorry, the beta gamma position. So attacks takes place from the gamma position to generate a stabilized carbocation at the beta to the silicon, because this silicon, the carbocation formed by the attack will be the beta. So I will show why this beta carbocation to the silicon is stable. So if you look at this case, so if you look by step, it is Si, and let's say these are Me3, right? Further, it forms a carbocation here, and now it has attacked on the this compound, right? So why this carbocation is stable? So first thing, the silicon, the lone pair, I will show the stability here. Why the silicon alpha position of the silicon is stable. So All right. So can you see this the intermediate step? So you can see the position in this case. Let's see here the carbocation form with the alpha position. Uh, sorry, the beta position. So to which the carbon silicon is attached. So this is the position. So if you just rotate the bond rotation, so you can see here the bond between the carbon and silicon and the carbon and carbocation. So this will be in the plane, and this stabilize the carbocation which form at the beta position to the silicon. So that's why it gives the stability to this carbocation, and that's the reason the attacks takes place in this case via gamma, not from uh, the other one. So not from this one, the beta. Further, we see you can see the acetylsilane also. So the acetylsilane is also one of the all right. So the acetylsilane. So how does it prepared? So if you can see here, let me. So if you add the butyl lithium, so or to the compound, this is the sulfur protected compound, right? So this is the protecting group. So it comes from this one. So this is the starting, and you can see the if you add the butyl lithium, it forms the anion over the place, and followed by if you add the trimethyl silyl chloride, so it generate silyl, and this is the obviously a synthetic equivalent of the uh, this formyl group, right? And in the upper case, if you add just butyl lithium, so it forms the anion, and obviously the upside the proton, and further by addition of the reagent here. So in this case, this is the chloride, right? So which has the electrophile. So this is the group. So this is the delta positive delta, and this is the chloride delta negative. So the anion forms which attacks on the chlorine. Sorry, attack on the carbon which attacks to the chlorine, and as a result we get the formation of the compound. So this is the entire this is the new bond form in this case, and initially it was the chloride group. Here there was a chloride. Now this new carbon-carbon bond getting formed. So and after deprotection, so what we get here? So this entire group gets removed and it forms a double bond. So yes, Mi see, and further this group can also we can able to uh, deprotect. So as a result, it forms here generate the hydrogen, and this entire group will be removed. So by this way, you can able to use the simple this formyl group attached. You can able to add at the position. So this is the reagent. You can see acetylsilane. Further, the one another reaction. So which is the metylation, silylation, and protonation of the methyl vinyl ether furnish a acetyl trimethylsilane. So you can see here. So if you add the butyl lithium and followed by the TMSCl, so it abstract the proton, followed give the uh, alkene silane, and upon workup, acidic workup, or the atomic treated with the slightly acidic condition and water, it gives the ketone. So this entire group get deprotected and it forms a ketone. So this bond goes to here and it abstracts the proton from the solvent. So this is the And what is the role of acetone? So in this case, acetone is the solvent mostly, most likely. So here, another reactions of this such compounds we can see here. This is the acetylsilane, right? So this is the acetylsilane compound, and that we have prepared earlier, the two slides back. So this is the acetylsilane. In this case, we have generated this acetylsilane, right? So this is the acetylsilane. So if you add the to this acetylsilane, if you add aryl magnesium alkyl magnesium bromide or uh, alkyl lithium, aryl lithium, so we can able to so in this case nucleophilic mostly. If you add the nucleophilic alkyl, it attacks on the center, the carbonyl center, and for the O negative forms on the oxygen, which attacks to the silicon, it gives the anion generation. So here the anion generated right over the. So initially, how what it was the polarity. So this bond polarity initially it was double bond O, right? So let's say when this X is equal to anything like oxygen or hydrogen or OH or OMe or I mean OMe, not necessarily OMe or NH2. So this center is generally delta positive and oxygen is delta negative, right? But by using this acetylsilium, what we can generate? We can generate the negatively charge. It's like a amplong. We can inverse the polarity by using such method. And you can see we generate an amplong here. And now if you add any kind of electrophile, so let's say if you add the electrophile, it attacks the electrophile and gives the electrophile here. So generally, we able to add only the nucleophile over the ketone, right? The carbonyl carbon of the ketone. But by using such amplong, generating such amplong, we can able to add the electrophile. And further, if upon protonation of this one, we can able to generate the hydrogen also here. So on any electrophile. So this is the method. So let's say if you have any electrophile, let's say the ethyl iodide. So in this case, you can see. So this is the simple compound acyl silane. We add the phenyl lithium. The phenyl directly attack on the this one, the carbonyl carbon, and generate the negative charge. So this negative charge further react with the ethyl iodide, use the ethyl substituted, and upon TBAF. So it is a tetrabutyl ammonia. So this is the TBAF. This is the nitrogen, right? And this is the plus positive and negative chloride. So this is the butyl group. So if you add the TBF, it helps to deprotect the silane and it generate hydrogen OH bond here from the silane. So the silane get deprotected over the steps by using the TBF. So these are the some utilities of this organosilane compound. So if you have any doubt, please let me know. So any doubt up to here? So if you have any doubt, please let me know. So we'll discuss that one. Right. So I will add some examples here and just show uh, the what is the product form of the reaction. I will not add the product. I will just only add the startings. All right. Right. So I have given the three questions here, and from these three questions, so uh, draw the what are the product from after this three. So this is the question. So in this one, we have added the secondary butyl lithium. We'll go from 3 to 1. Secondary butyl lithium that we have added, or the third butyl lithium. So it generate obviously it acts as a proton from here, right? And it generate the cation, so which is at the positions here. So once it generate the cation, so it forms the either cation generate or either it might be on the this is the alpha, beta, or the gamma. So it will delocalize in between this case. And when you add the ketone over this one, so what is the product? So you have to tell the what is the product getting from. Further, in the second question, you can see here. So we have added the aldehyde. So this is the aldehyde, right? And upon addition of the Lewis acid here, so it generate the delta negative here and delta positive. So definitely how this reagent react over this on aldehyde in place of Lewis acid. And the first reaction is here is the when you add the BF3 ethylate over the compound, that's also the Lewis acid. How does it show the reactivity? So, so these are the some questions. So hope you able to solve these questions. If you have any doubt, let me know. I will help you solve this one. All right. So I will give the answers for all of these questions. Right. So in the first question, what it is mentioned, we have added the here allyl silane, right, with the Lewis acid. And in the compound itself, we have right. In the compound itself mentioned the BF3 ethyrate, right? So when this silane react with the BF3 ethyrate, that is the Lewis acid, it generate a cation. With this BF3 ethyrate, it get polarized here, right? So I will directly show the wait a minute. So what happens? This will be the BF3 here, right? So it is getting polarized. It forms the bond, and after that, it attacks via. So this here it is the ketone is getting formed, and so at this position, so this is the product form. So the mechanism. So you have to work out how this get product is getting formed. In the next step, next question, this is the methyl group here, which has the olefin, and then followed by the this is the vinyl silane. It react with the aldehyde in presence of Lewis acid. So it forms a methyl. So this product is getting formed. So forget about the stereochemistry in this case as of now, because if we discuss the stereochemistry, then that the discuss different case, different products here. But as of now, so this is the product form after this reaction. And in the last reaction, the third question, so it forms a lithium, right? And when it reacted with the uh, this ketone, so what happened? It directly attacks on the carbonyl carbon, right? So the product is in this case will be alcohol, and which has the so this is the product form after this case after the treating with the cyclohexanone. So these are the some of the examples. So hope you will see some more questions I will add in the PPT, and you can see that in the OneDrive. So we'll stop here for today, and again come back uh, in the next week. So if you have any doubt, please let me know.